All right, guys, welcome to our review video for Unit 4. So this is our third video, I believe, on differentiation. And this one has to do with application type questions. And so does the fifth one as well. But they broke it up because I think there's just a lot of content there. So we're going to talk about applications of derivatives. In other words, what do you do with these derivatives? All right. Well, one of the things is when you're using derivatives to solve problems or word problems, you need to understand how to interpret them and what they mean. So here's an important point for number one. Is talking about the units. If the units of f of x are y, and the units for x are t, so the function has units of y, and the units for x are t, then the units for f prime is going to be y over t, the y units over the t units. So let's give an example for that. Well, before I do, we'll talk about the second derivative. So then the second derivative would be y per t per t. So every time you take a derivative, your whatever units are the inside variable, in this case t, every time you take a derivative, you get a t unit on the bottom. So the first time you take a derivative, you get 1 t unit on the bottom. The second time you take a derivative, you get 2 t units on the bottom, so it becomes squared. And if you did the third derivative, it'd be units cubed on the bottom. Or you could say it, instead of saying y units over t units squared, you could say it in English like this, y per t per t. Or if you did the third derivative, it'd be really fun to say y per t per t per t. We're starting to create another language here, aren't we? All right, so there you go. So here's an example. Let f of x represent the population. So f of x, the output variable, is population of people in a city per thousands. Okay, so if f of x is 5, that means there's 5,000 people in the city at that time. And let's say the input variable x represents the number of years. Then what does this mean? F prime of 4, well, I already know what the units are going to be. It's the output units over the input unit. So the output unit is the population. So this means there's going to be people. That's the population we're talking about. And then the input units is years. So in other words, people per year. So what does this mean? Since there's a 4 in there, that's in the place where the x is. So that's a time. That's the number of years. So the interpretation of this expression here is at t equals 4, the population is changing at a rate of blank. It didn't say what it equals, so I don't know what the f prime of 4 is. But it says, at a rate of blank people per year. So at t equals 4 years, the population is changing at a rate of blank people per year. Now, I actually don't prefer to word it this way, but we're working with limited information, so I can't help but word it this way. But typically what I like to do is we like to have either a positive number or a negative number. Okay, if it's positive, that means the population is increasing, and if it's negative, that means the population is decreasing. Okay, and so we prefer to use that kind of language rather than just say changing, but changing is fine. You can say it that way, but we do prefer to say increasing or decreasing based on whether the outcome is positive or negative, right? So what would this one be? This is people per year squared, okay? Because it's the second derivative. So how would this interpretation work? This one would be at t equals 4 years, that's because the number on the inside is 4. The rate at which the population is changing, that's the first derivative, is changing at a rate, now that's the second derivative. So the rate at which the people is changing is the first derivative, so that's f prime. But since there's another prime, that's the rate of the rate. So the rate at which the population is changing is itself changing. at a rate of blank people per year, because it's people over year squared, right? So you say per year. So that's how you interpret derivatives in context, okay? And just so you guys know as a side note, sometimes in the problems that they give you, the original function is already a rate. So they might give you a function that's a rate anyway. So when you find the first derivative, that's actually more like a second derivative because the first one is already a rate. So then you would word it like f is changing at a rate of, but f is itself a rate. So it's like a rate is changing at a rate of. So keep that in mind. But let's go ahead and move on here. All right, guys, so next slide here, we'll talk about how to find or estimate the value of a derivative when you're given a graph, a table, or an equation. Now, the equation is the most common one that we do in here. Obviously, if you want to find the value of a derivative, you apply the appropriate derivative rule. So like, if I had y equals x squared, then we would apply the power rule, right? When we get 2x, and then just plug the number in that they want you to find the derivative at. So that's how you do an equation. But whenever you have a table, you can't get the actual value. So what you end up doing is you end up picking two values that are really close to the one that you want, and you do the f of b minus f of a thing. Write that out real quick. So with a table, you're not getting an exact answer for the instantaneous rate of change. What you're doing is you're getting an estimate of the instantaneous rate of change by doing the average rate of change using 2 points that are closest to the point they're asking about. Next we have finding a derivative on a graph. So if you're dealing with a curve, what you want to do is you want to sketch the tangent line at that point and just find its slope. A lot of times though, you'll be working with say like a piecewise function or something, and the slope of the lines is obvious because they're just straight lines anyway. In that case, just find the slope. Remember, it's rise over run, and that's how you find slope. Okay, going down or left are negative values, but going up and right are positive values. So rise over run. So for a graph, rise over run. For a table, pick two values closest to it and do the average rate. And for an equation, find the derivative and plug the number in. So those are three methods for finding the values of derivatives, depending on what kind of stuff you're given to begin with. Another topic we'll talk about in this lesson is linear approximations. A linear approximation is when you use a straight line, which is usually the tangent line, to estimate the values of a curve, f of x. Okay, so how do you use a linear approximation? Well, let me just give you guys a picture of it first. So like, for instance, if you have this curve right here and you draw a tangent line at a specific point, as you guys can see on this entire area here, and even going out a little bit further, the blue line and the red line are so close together that they're almost the same, right? And so that's the idea. Doing math with curves is a little bit more complicated than doing math with straight lines. And so what we do is we do linear approximations. That means we can estimate what points are and what slopes are on this red line by looking at slopes and points on this blue line, because it's a little bit easier. And what that requires us to do is to find a tangent line. So how do you do a linear approximation? Well, step one is to find the equation of the tangent line at x equals c at the point that they give you. Next, you're going to be estimating the value of your function at some point. We'll call it d. Now, so long as d is close to c, then f of d is going to be roughly equal to the value of your tangent line at d, because your tangent line is really close to your curve at that point. So the value of your function at d will be roughly similar to your tangent line's value at that point because they're so close to each other. Next, we have some interpretational issues. So they're not going to be exactly the same, but they'll be close. So sometimes the function will be greater than the tangent line. When that happens, that means that your graph is concave up. So if you have a concave up function, then your tangent line is underneath of the curve, and therefore the f is greater than the y, and that means your graph is concave up. Now, another way you could say that is the second derivative is greater than 0, but they both mean the same thing. Now, if your function is less than your tangent line value, then your function would be concave down, or the second derivative would be less than 0. A little interesting point to point out is that the place where your tangent line actually touches the curve, at that one singular point, both the slope and the y value of the tangent line are exactly identical to the slope and y value of your curve. That's because at that point they're actually the same. It's just that as you start to get away from that point, they start to gradually get less and less the same. Okay, and so that's what a linear approximation is. So let's go ahead and move on to a new topic here, motion problems. This is a really important topic for your AP exam, real important. Sometimes they have an entire FRQ just devoted to these alone. So there's a whole lot of stuff we could talk about here. So let's say that F represents the position of an object at time t. All right. Well, then F prime is its velocity. In other words, F prime will tell you the direction the object is traveling, and it will also tell you its speed. So if it's a positive number, then that means that your object is moving either to the right or in an upward direction, depending on if you are on a vertical or horizontal axis. And the bigger that number is, the faster it's moving. Okay, so F prime tells you direction and speed. Now, if you just take the absolute value of it, that gets rid of the plus and the minus, and then you're just looking at speed only. So the absolute value of F prime is speed. The second derivative tells you the acceleration. It tells you how fast the velocity is changing. I should have put velocity here instead of speed, but now when you integrate it, now just so you guys know, this lesson is not really supposed to focus on integrals at all. It's supposed to focus mainly on derivatives, but I figure these types of questions go together so often it's worth talking about. In our last unit, Unit 7, we talked about this stuff. The integral of the derivative from a to b is the displacement of your object that's moving. In other words, if you integrate this, you get f of b. So the integral of f prime is f. And you plug in the upper number, and you also plug in the lower number, and you subtract those. Well, what is f of b? F of b, well, f is the position of the object, so f of b is the position at the final time, and f of a is the position at the starting time. So your displacement is basically the distance between your final position and your starting position. And once again, these can have signs associated with them. So if you end up with a positive number here, that means that your object is to the right of its starting point. If you end up with a negative number, that means that your object is to the left of its starting point. Or you can change that if you're talking about a vertical axis to above and below. But that's what the integral of f prime represents, is the displacement. Now, when you take the integral of the absolute value, that tells you the total distance traveled, okay? And there is a difference between those two things. I mean, if you have an object that's moving along a straight line like this, and let's say it starts like right here, well, let's say it goes this way for a little bit, and then it comes back, and then it goes over here, and then it goes back again, and it stops here. Well, the displacement is the distance from here to here only, okay? But the distance is the total length of this squiggly line that I'm drawing. And so that's what the distance is the absolute value of the derivative squared, okay? Finally, you can create a position function. Now, if they tell you the position function up front, you don't need this equation here, okay? But a lot of times with these types of questions, they're going to give you the velocity function, which means they're going to give you f prime instead. And so if they give you the velocity function, then you can create a position function by writing the displacement formula and adding to it the initial or starting point. That means you have your starting point plus your displacement, and that will give you the final position. So this is what we call a position function. So you would only need to create this if they gave you the velocity function to begin with. If they gave you the position function to begin with, there's no point in creating a position function. They gave it to you, right? So those are some really key and important formulas, and understanding what those formulas represent when it comes to motion problems. All right, so another thing that we want to think about when we are dealing with motion problems is interpreting f of c, f prime of c, and f double prime of c, specifically looking at their signs. So let's start by looking at the f function, in other words, the position function. So if you're on a horizontal axis, a positive value means that we are to the right of the origin. A negative value means that we are to the left of the origin. 0 just means you're at the origin. Now, if you're on a vertical axis, a positive number means you are above the origin, a negative means you're below, and once again, 0 means you are at the origin. So that's for position. It just tells you whether you are where you're located on the number line, basically. Now, f prime is velocity. Velocity has to do with movement. And so it's not talking about where you're located, it's talking about what direction you're moving. So if you're on a horizontal axis, then if your velocity is positive, that means you're moving to the right. If it's negative, that means you're moving to the left. And if it's 0, that means the object isn't moving at all. On a vertical axis, a positive velocity means moving up, a negative velocity means moving down, and 0 means, again, still means not moving. Finally, we have acceleration. Now, this one's a little bit more difficult to visualize. It doesn't really matter if you're on a horizontal or vertical axis for these ones, so there's no mention of that here. Basically, if you have a positive acceleration, that means your velocity is increasing, which can mean one of two things. It means that if it's positive, it's becoming more positive, or if it's negative, it's becoming less negative. Okay? In both of those cases, the velocity is increasing. If your acceleration is negative, that means that your velocity is becoming more negative. So if it's already negative, it gets even more negative. Or if your acceleration is negative, your velocity is decreasing. That could also mean that if you have a positive velocity, it's becoming less positive. So that's the idea there. Now, if you ever have an acceleration that is 0, that means your object is still moving. It just means that its velocity is not changing. So the velocity is constant. It's like you're moving at a constant speed, in other words. So that's what all that means, interpreting f, f prime, and f double prime in the context of positives, negatives, and zeros, especially thinking about whether you're on a horizontal axis or vertical. So this is a nice little reference chart to keep on hand. Another thing that is really common with these motion problems is they'll talk about, is the object speeding up or slowing down? An object is speeding up anytime the velocity and acceleration are the same sign. So if they're both positive or if they're both negative, then your object is speeding up. And the way that I explained that in class was, imagine that you are a runner. Yes, we go that way. There we go. You're going for a jog, and somebody's got like a rope that they tie around your waist and they pull you. Well, you're running to the right, and they're pulling you to the right, so what's going to happen? You're going to speed up, okay? Or opposite, we could flip it around. If you're running to the left and they pull you to the left, you're going to speed up. Acceleration is like the pull. So if they're pulling you to the right, that would be like a positive acceleration. And if you're running to the right, that's like a positive velocity. So since they're both positive, in other words, they're both going in the same direction, you will speed up. Now, if an object's velocity and acceleration are opposite signs, the object slows down. So I mean, once again, imagine that you are going for a jog, and you're moving to the right, so that means your velocity is positive, but now that person with the rope is pulling you this way. Well, that's going to slow you down, because now you've got a negative acceleration pulling you to the back way, and you're going in the forward way with a positive. So if they're opposite, you slow down. So that's kind of how I explained it initially. All right, so let's talk about motion problems. Now, these problems can be asked with tables, they could be asked with graphs, or they could be asked with equations. So, and they're very often asked with graphs. So let's go ahead and start there. If you're given the graph of a velocity function, which is usually the way it works, it's not common for them to give you the graph of the position function or the acceleration function. It's more common for them to give you the velocity function, because there's a lot more questions you can ask about that type of situation. So If they give you the graph of the velocity function, then as you guys know, velocity is positive when the graph is above the x-axis, because anytime this graph is above the x-axis, that means that those are all positive velocity values. And it would be negative anytime the problem is below the x-axis. So that would be like here, for instance, that's a negative velocity. Now, if this wasn't a velocity graph, if it was a position graph, that you'd have a totally different situation on your hands, because well, it just depends. But in the case of any function they give you, anytime it's above the x-axis, it's positive. So since this is a velocity function, since it's above the x-axis, that means velocity is positive. All right. Now, acceleration, as you guys know, is the derivative of velocity. Now, derivative is just a fancy word for slope. So acceleration is positive when the slope is positive. So for instance, since this is a velocity graph, the slope of this line is positive here, so that means the acceleration is positive. We also have a positive slope here, so that's another place where acceleration is positive. Right? Now acceleration is negative when the slope is negative. So on this graph we have a negative slope here, and we also have a negative slope here. So both of those are places where the acceleration would be negative. This flat line means that the slope is 0, so the acceleration is 0. And when acceleration is 0, that means that you have a constant speed or a constant velocity. It's not changing. Okay. Next, going back to integrals once again, the area under the curve will give you the displacement. So, we talked about how this is displacement, right? The integral of your derivative or of the position function, in other words, the velocity. The integral of velocity gives displacement. So if I were to say to you, what's the displacement from 0 to 2? Well, on this graph, that would be the area under the curve from 0 to 2. And that, whatever that is, that will tell you the displacement. Since all this is a positive area, that means that your object by the end of those first 2 seconds would be somewhere to the right or above where it started. If you did the displacement on this interval, it would be to the left or below, because that's a negative area there. Now, if you ever wanted to find the total distance of your object, then you do the same thing, find the area under the curve, but this time you just take the absolute value of it. So if you wanted to figure out how far this particle traveled, you would be doing the integral of the absolute value of velocity from the very beginning of the story to the end of the story. And what that means on this graph is just all these areas added up. And just make sure that when you do it, you don't make this negative, even though it is below the x-axis, because we are doing absolute value, which is distance. So you just make them all positive. So that's how you can find distance and displacement, acceleration and velocity when you have a graph of a velocity function. Okay? All right, next topic. We're going to talk about related rate questions. Related rate questions are questions where you're given one rate and then you are asked to find another rate. The steps on how to solve this are given here below. So a lot of times the first thing you're going to do is draw a picture. On your picture, you might want to label the values that don't change with numbers and the variables that do change with letters. So keep that in mind. Next part. Identify the given rate and determine if it's positive or negative. So like I said, you're going to be given a rate, and you have to ask yourself, is it positive or negative? Are they talking about something that's increasing or something that's decreasing? So if it's positive, it's probably going to say something like the object's amount is increasing. If it's negative, they'll probably be saying it's decreasing in some way. Okay. Then you want to make sure that you are aware of what rate it is you're trying to find. That's helpful. Now, once you've done steps 2 and 3, you know what rate you're given and what rate you want to find. Those each have a variable associated with them. So, let's say this one was X and this one was Y. I don't know. You don't need to write that on your paper. I'm just giving you an example. Well, your job is to create a formula that connects those variables together for step 4. So you need to create a formula. That's one of the hardest parts of these problems, is creating the formula, because sometimes they'll give you the formula. That's really nice. In fact, I'd say more than half the time they do. But sometimes they don't. And so creating it requires you just to know like some basic geometry usually, or something like that. But once you have that formula, you're going to take the derivative of it with respect to time, and that means with respect to t. And t won't match either one of these, so make sure that as you are doing this, it's implicit differentiation. You're going to get, when you take the derivative of something with a y, you're going to get a y prime after it. And when you take a derivative of something with an x, you're also going to get an x prime, because neither one of these will match the variable of differentiation. And so it will be an implicit differentiation. The last few steps are to find all the missing values that you need for this formula to be complete. And then finally, you should be able to solve for the one desired rate that you're looking for. So there's our steps. Draw a picture, know what rate you're given and what rate you're trying to find, and make a formula that connects them. Find the derivative of that formula and plug in everything you have so you can find the one thing you don't. And that's how you solve a related rate question. So here's an example. A 25-foot ladder is leaning up against a wall. The base of the ladder is sliding away from the wall at a rate of 3 inches per second. How fast is the top of the ladder sliding down the wall when the base is 15 feet away from the wall? So step one is to draw a picture. You do want to do this on your notes, by the way. So here's my ladder. It's 25 feet tall, and here's the wall it's leaning against, and here's the ground. Now, notice I put 25 where the ladder is because in this story problem, the length of the ladder is not going to change. It's going to constantly be 25. But the height of the ladder up the wall, that will be changing. In fact, it's going to be decreasing because the ladder is sliding down the wall. The base of the ladder, I'm going to call that B, that's actually going to be increasing because it gets farther and farther away from the wall as the ladder slides down. So I'm going to put letters for those ones because they are changing. But notice for the ladder, I put a constant because in this problem, the length of the ladder is not going to change. All right, and so that's step one, is to draw your picture. Step two, and this is, you got to add these things to your notes once again, is to identify the rate that they give you. They tell me that the base of the ladder is sliding away from the wall at a rate of 3 inches per second. So B is the one that's changing, the base of the ladder, or the base of, from the base of the distance of the ladder from the wall over time. So dB dt, and notice I put positive 3. That's because it's sliding away from the wall, so that distance is increasing. Okay, so that's my given rate, and then my desired rate is dA dt. That's A represented the height of the wall, and so that's the one that is going in a downward direction. So that was A, so dA dt. Now, whenever you have a picture that looks like this, right, we had an A here and a B here and a 25 here, we got to find a way to connect these variables together in a formula. And when we did this lesson a little while back, can you guys remember what formula we connected those with? We connected those with the Pythagorean theorem. So that would be a squared plus b squared equals 25 squared. So now I've got an equation with both a and b in it, the one I'm given and the one I want to find. But I don't want just a and b, I want dB dt and dA dt. So for step 5, we take the derivative. Now if I take the derivative of a squared is 2a, but you have to put an a prime next to it, in other words, dA dt. The derivative of b squared is 2b, but we have to put a b prime next to it, in other words, dB dt. And this is just a constant, 25 squared, so that's just 0, so we can get rid of that. Step 6 is to find any of the missing values that you need. So they already told us that b is 15, the base of the ladder is 15 feet away from the wall. They also told us the rate of change of a. Oh, this was supposed to say b. That's another thing I need to fix. They also told us the rate of change of b with respect to time. That's 3. All right, and then there's one other thing that we need, though. Remember, my goal is I want to figure out what is dA dt. And right now, I know what b is. B is 15, right? I know that dB dt is 3, so I know what this is. But I'm still missing a. So I need to figure out what a is before I can find out what this orange piece is here. And so that'll happen sometimes where you need to find one more thing that's not actually given to us. And the good news is we could just use Pythagorean's theorem. So a lot of times if you're missing something, just go back to your equation from step 4 and plug in whatever you can there to find the missing piece. So in this case, you could plug in the b equals 15 here, and you can solve for a. In that case, we find out that a is 20. So now that we have all the pieces that we need, we have the a, the b, the dt, we just need to find the dA dt. So if we plug all those things in, it would look like this now. And then in step 8, we just go ahead and solve. So there's your rates of change, right? You do a formula, identify your given rate, the rate you want to find, create a formula that connects those variables, take the derivative of that function with respect to t, identify all the stuff that you need and are given, plug it in so that you can find dA dt, and that's it. So that's related rates. All right, I think we got one last topic to talk about in this lesson, and that's rate in and rate out questions. We just got through talking about those in Unit 7, so hopefully that's fresh in your mind, but let's review it. Rate in, rate out questions are problems where you have one rate that is increasing some quantity, and rate out, the other rate, is a rate that is decreasing the quantity. And when I taught this, I gave you guys the example of a bathtub where water was pouring in, but also there was a drain, so water was coming out. Now, typically in these problems, they will give you a starting amount. Okay, so they'll tell you how much is there to begin with, but you know how fast stuff is coming in, and you know how fast stuff is going out. And that's a rate in and rate out question. And I gave you this nifty little chart too back then. So let's talk about that. Let's say that my rate in equation is I. Okay, and let's say that my rate out question is O. Okay, now both of those have units that, if we just want to stick with, it's going to be an amount over time. So like, for example, in the case of a bathtub, you could say liters per minute or something like that. But that's what those units would be for those particular problems. Now, if you take the rate in and you subtract from it the rate out, that will tell you the total change in the total or net rate of change. So, let's say water's pouring into the bathtub at a rate of like, I don't know, let's say 15 liters per minute, and it's draining out of the bathtub at a rate of like 10 liters per minute. Well, you subtract those, you get 5 liters per minute. And since it's positive, that means the rate in is greater than the rate out, which means that the amount of water in the bathtub is increasing because it's positive. Okay, so you have rate in, you have rate out, and when you subtract rate out from rate in, you get the total or net rate of change of the amount in the tub over that time, right? Now, if you ever want to find how much water is added in, or whatever quantity you're measuring, you integrate the rate in. So if you integrate that rate in on the interval from A to B, that will tell you how much has been added over the time interval A to B. Now, we talked about derivatives and units, right? When you have a derivative, if you have a function, when you take the derivative, you get another time unit added to the denominator. Well, integration is the opposite. So every time you integrate, you lose a time factor off the denominator. So if the units for rate in is an amount over time, then the units for the integral of your rate in function is just going to be an amount. In other words, this will tell you a certain number of liters that were added over a certain period of time. So the unit would be liters only. So like this one would be liters per minute. This would just be liters. If you want to find out the total that was lost over a certain period of time, you would integrate the rate out function over that time period. And then if you want to find what the total change in the amount was over time, then you would do both of those things combined. How much was added, how much was lost over that time period. And that tells you the total or net change in the amount. So this is the total rate of change up here. This tells you the total rate. This tells you the total amount. Okay, so that's that. Now, we also, from this, can create a formula that will tell us the total amount in the tub at any given time. So you can find the total amount in the tub at any given time, we'll say B, so long as you know the total amount at the beginning, which once again, usually you do, and you add to that the net change. In other words, how much the water changed based on how much was going in and how much was going out over the time period in question. And so this is our total amount formula. And you'll notice this looks a lot like the position formula for motion problems, and it's because they really are the same thing. One's just talking about distance and speed, whereas this one's talking about a quantity of something else over time. It's the same idea though. All right, and that'll do it for our lesson. So all those concepts will be in this unit's practice this week. So we'll see you guys in class. Until then, have a good one.